Hello everyone, this is Guillermo Peñafort from Universidad Nacional Autónoma de México, and I'm going to talk about some joint work with Farid Tari on k-folding mappings and robust features of surfaces in R3. Let me tell you a little bit how we started this thing. So 3 years ago, I was giving some seminars there in San Carlos about reflection mappings. And reflection mappings are a generalization of folding mappings, which are some singular maps that describe what happens when you take a surface in R3 and you fold it along a plane. As I was giving my generalization of that, Farid made a comment. He said, you know, Guille, there is this work by Bruce and Wilkinson where they are able to detect robust features of surfaces by looking at what kind of k-folding mappings you get on different points and different directions. So what happens if you do the same with your generalized folding mappings? What would you detect? And I just didn't know the answer to that question, and I just didn't know what he was talking about altogether. So I probably replied something polite at the moment, and my natural reaction would have been just to try to avoid Farid at all costs forever after that. But that didn't happen, thankfully, and we started looking at the problem. So now, 3 years later, we know the answer. So today, what I'm going to explain is the strong and, to me, very surprising connection between robust features and k-folding mappings. Let me show that now I know what robust features are by giving you one example. Say that you're given a surface in R3, like this torus. There will be a region called the elliptic region where the surface looks locally like a cup. What this means is that if you place the tangent plane on an elliptic point, the surface will stay on one side of the plane, at least locally. And then the opposite happens on the hyperbolic region, where the surface looks locally like a saddle and it crosses from one side of the tangent plane to the other. And the elliptic and parabolic regions, they form open subsets and cover all the surface except for a curve between them. This curve is called the parabolic curve, and it is one of the robust features we will be looking at. Now, what does it mean that the parabolic curve is a robust feature? Well, for something to be called a robust feature, it requires two things. It has to be an extrinsic differential geometry object. What that means is that it has to be preserved by rigid transformations of the ambient space. And second, and this is why we call them robust, if you deform your surface slightly, the parabolic curve will deform also slightly, and then you will be able to follow it as it moves. Now let me list the robust features that we will consider today. I didn't say it before, but actually the parabolic curve is divided in two curves. There is the red parabolic curve and there is the blue parabolic curve. There are also red and blue subparabolic curves. There are also curves that come in one color, like the ridge and the fleck-nodal curve. And then there are also isolated robust features. There are the umbilic points, the special A asterisk points on the parabolic curve, and the butterfly points on the fleck-nodal curve. What these robust features have in common is that they can be defined in terms of the contact of the surface with lines, planes, and spheres. Now let's see what these folding mappings are. First, we need to understand what it means to fold the ambient space. This is done by means of the Windy fold. The Windy fold is a mapping from Rn to Rn that takes a point and it squares one of its coordinates. If that coordinate is called y, this corresponds to folding the space with respect to the y equals 0 hyperplane. And then it identifies the points xy and x minus y. Of course, there is nothing special about the y equals 0 hyperplane, and there is a Windy fold for every hyperplane pi in Rn. Okay, so that was the Windy fold. What is a folding mapping? Okay, say that you have your surface M embedded in R3, and then for every point P in M and every plane pi going through the point P, you're going to take the Windy fold with respect to pi, you're going to restrict it to the surface M, and then you're going to take the germ of that at the point P. That will give you a germ from the manifold to R3. In this case, we see a folding mapping that it parameterizes a crosscut. And you see that the crosscut is exactly what you get if you take the surface M and you fold it along the plane pi chosen there. Now, what is very easy to see also is that any folding mapping can be taken by a change of coordinates to a map germ from R2 to R3, of the form xy maps to x y squared f of xy. So the good thing is that we know these mappings very well. These folding mappings appeared in the classification by Mond of all simple mappings from R2 to R3. For instance, we know that all folding mappings up to codimension 4, they have to be members of the families SK, BK, and CK. So the plan is we are going to take a surface, we are going to fix a point, and we are going to say something about the point in terms of what kind of folding mappings we find when we move the reflecting planes. Let me call V the orthogonal direction to the reflecting hyperplane. The first thing that you notice is that if V is not tangent to the surface, then the folding map that you get is an immersion, regardless of the geometry of the surface. So the only interesting planes are those whose orthogonal direction is tangent to the surface. Now take a plane whose orthogonal direction V is tangent to the surface. If V is not a principal or an asymptotic direction, then what you will get is a crosscut. And then on the principal or asymptotic directions, you will get something more degenerate than a crosscut. And that is where the interesting information lies. So for instance, for most points of the surface, what you get is immersions, crosscuts, and then on the special directions, you get an S1 singularity. But for instance, if you are in the subparabolic curve, you will get immersions, you will get crosscuts, and then you will get an S2 singularity instead of the S1 singularity. And then there are special points on the subparabolic curve where you get an S3 where you were supposed to get an S2. These points where you get an S3 are a new robust feature that was discovered by Bruce and Wilkinson exactly that way, and they are called the S3 points. Something similar happens on the ridge. You can detect the ridge by the fact that instead of S1, you get an B2 singularity. And on the ridge, there is a new robust feature called the B3 points, where you get the B3 singularity instead of a B2 singularity. Also, you can detect where the ridge and the subparabolic curve intersect, because on those points you will get a C3 singularity instead of the S2 singularity coming from the subparabolic curve and the B2 singularity coming from the ridge. This is the work of Bruce and Wilkinson that Farid mentioned in that seminar. They show how to detect some robust features by looking at folding mappings, but not all. There are robust features that cannot be detected by looking at folding mappings, like the parabolic curve and the Fleck-Nodal curve. From the point of view of folding mappings, they are just generic points on the manifold. Back to Farid's question. What would happen if you were to use generalized folding mappings instead of classical folding mappings? So the first thing we need to learn is how to fold the ambient space k times instead of 2. And that is done by using the order k-fold instead of the Whitney fold. The order k-fold with respect to the y equals 0 hyperplane is a mapping from Cn to Cn that takes a point to the same point where the ith coordinate has been replaced by its kth power. And of course, for every complex hyperplane of Cn, there is a Whitney fold, there is a k-fold associated to that. Instead of gluing 2 points like the Whitney fold does, the order k-fold glues k points. If you let C be a primitive kth root of the unity, then the collection of points that end up identified are obtained by multiplying the y coordinate by powers of C. Of course, this geometric interpretation is only possible in the complex setting, So that's why it's important that we use Cn instead of Rn as an ambient space. Now that we know how to fold the space k times, the general k-folding mappings are obtained in pretty much the same way as the usual folding mappings of order 2. If we are given a surface M in R3 and a point P in M, we can take the complexification of M around P, and that defines a germ of complex surface in C3. Here, I am assuming M to be analytic for simplicity. There is a fix to make this work for C-infinity surfaces, but we are not going to look at that now. Next, when you give me a plane through P, I can also take its complexification. And now we can do the same as we did with folding mappings. We restrict the k-fold map with respect to the complex plane to our complex surface. And we take the germ at P. Again, we have a very easy normal form. Every k-folding mapping is A equivalent to a germ of the form x, y to the power k, and then f of x, y for some function f. So then Farid and I started looking at what kind of k-folding mappings you can get on surfaces. And pretty soon we discovered that we have a serious problem. Most of these k-folding mappings are not simple. And this is a problem for two reasons. First, these singularities have not been classified. The most well-known classification of mappings from C2 to C3 is Mond's classification, which contains simple mappings and mappings up to codimension 6. And our guys, they do not fall into these categories usually. Secondly, we found out that for k greater than 3, a generic manifold will produce infinitely many different A classes. And moreover, if you deform the surface a little bit, these classes will change. So now you cannot trace a robust feature by saying, okay, I'm going to follow this particular A class, as Bruce and Wilkinson could do. But then we realized that even if there are infinitely many A classes, many of them will represent the same topological A class. Let me remind you that two map germs are said to be topologically A equivalent if you can pass from one to the other by means of homeomorphisms in source and target. Then our idea is we are going to classify all the k-folding mappings that can appear on a surface topologically. And then we are going to see where the different topological classes show up. Our approach is based on some recent results on topological invariance and the ways to compute them. For any map germ f from C2 to C3, there is the double point curve D in C2. We can take the Milnor number of D, or we can just count the number of irreducible components that it has, which is the number Rd here. We have other numbers like C, which is the number of crosscaps that appear after taking a stabilization, or T, the number of triple points on a stabilization. The first result I want to mention is this. Since they were introduced, these numbers were known to be A invariant. But last year, Javier Bobadilla, Edson Sampaio, and I showed that they are actually topologically invariant. However, we found out later that this result could be recovered just by combining previous works from Le, Nemeti and his student Pinter, Siersma, and Van Straten. So we ended up just writing a note and uploading it to the archive. The point is, now we know that if two mappings are topologically A equivalent, then all these numbers must be the same for both. And then there is the result of Javier Bobadilla and Maria P., which is a theorem for families of map germs that goes in the opposite direction. If you have a family of map germs and the Milnor number of the double point curve is constant, then the family must be topologically trivial. Therefore, changes of topological class correspond to jumps of the Milnor number of the double point curve. It is clear that this double point curve is the object we want to be looking at, but the problem is, in general, it is very hard to compute. Here is where understanding the geometry of k-folding mappings makes all the difference. So say that this is your double point curve. What we have shown is that the double point curve of a k-folding mapping decomposes as a union of k-1 branches, and each of these branches is given by the vanishing of an explicitly defined function lambda j. With this at hand, you can compute the Milnor number of D in terms of the Milnor number of each of the branches together with the intersection numbers. Similarly, the triple points can also be computed directly from the functions lambda j. These expressions for the Milnor number and triple points are much simpler and easier to control than any other way of computing these numbers. Now you combine the topological invariant results with the explicit expressions that we just saw, and you put there a lot of brute force and you will get our main result. Take a number k. If M is a generic surface, then all k-folding mappings exhibited by M are finitely determined and represented topologically by the following classes. In other words, at the level of topology, generic surfaces can produce only so many different k-folding mappings, and we have the complete classification. Now, let's see what they tell us about robust features. Things start very similar to the folding mapping case. If you're looking at a non-tangent direction, you will get an immersion, which is an M0. If you look at the tangent direction, which is not asymptotic nor principal, then you will get an M1, if and only if again. And then on the asymptotic and principal directions, you will get something more degenerate, and that is where the fun begins. On generic points, this more degenerate singularity, it will be an M2 singularity. But if you are on the subparabolic curve, the more degenerate singularity, it will be an M3 singularity. And if you are on the ridge, it will be an N3 singularity. Then for the special points, on S3 points, you will get an M4 singularity. And on B3 points, you will get an N4 singularity. And then on the intersection of the ridge and the subparabolic curve, that is on the C3 points, you will get an O4 singularity. So all the robust features that we were able to detect before, we can still detect them with this generalized construction. What about the robust features that we couldn't detect by using folding mappings? On the parabolic curve, you will get a U3. On the flecknodal curve, you will get a Q3. And then for the special points, on butterflies, you will get an R4. On A asterisk points, you will get a U4. And then notice, the parabolic and subparabolic curve, they can meet with same color, that is red and red or blue and blue, or with different color. If they meet with same color, you will find an X4 singularity. And if they meet with the different color, you will get a W tilde 4. So, all these robust features that have to do with contact with planes, lines, and spheres, they all can be detected by using k-folding mappings. But there is more. We found a new curve, which we call the H3 curve, because in the case of k equals 3, you will find an H3 of Mond singularity, but in general you will find a P3 topological class there. And that curve has interesting properties. It passes through the points where the parabolic and subparabolic curves meet, but only on the points where they meet with different colors. And then it also passes through these A asterisk points. And then we found a couple of special points which are new. We found H4 points on our new H3 curve. In general, on them you will find a P4 topological singularity. And then we found new V4 points on the parabolic curve, and we found Q tilde 4 points on the flecknodal curve. And all these new points are points where we still don't know what differential geometry interpretation they have in terms of contact. Let me summarize a little. The robust features that we already knew how to detect with folding mappings, now we know that we can detect them with k-folding mappings. Okay. The robust features that we cannot detect with folding mappings, now we know that they can be detected with k-folding mappings as long as k is higher than 2. And this is nice because these higher order folding mappings, they are not detecting random things. They detect the robust features that we already care about. And then they give us some new robust features that we still don't know the interpretation in terms of contact. So I think the answer to Farid's question is that yes, there is a lot of things that these k-folding mappings can tell you about the robust features of surfaces. Okay, that is all I wanted to say. And if you want to leave any question in the comments, or if you meet me somewhere and want to ask something, I promise you I will try to take a little bit less than 3 years to answer. Goodbye.